This video, we're going to fill in the blanks for the Class 20 handout, which was about Diels-Alder. Diels-Alder is a natural extension from what we talked about in the previous class, which is the addition of HX to conjugated dienes. Because in the Diels-Alder reaction, we are using a conjugated diene and reacting it with a dienophile, a molecule that wants to react with a diene. On page 1 of the handout, I went through the MOs of the diene and the dienophile. It seems pretty comprehensive. I don't know if there's anything else that I want to talk about in this case. I do want to add, though, that the example of the MO overlap that we saw in class, it looks like we get good overlap between the HOMO of the diene, and just remember that is called psi 2, with the LUMO of the dienophile. And that name of the LUMO is pi star CC. So those are the official names. Now, for a reaction to happen, it's always going to be the HOMO of one molecule combining with the LUMO of another. Or I shouldn't say reaction, but whenever you're making a bond, okay, it's going to be the HOMO of the, typically the nucleophile, and the LUMO of the electrophile. But in this case, we have diene and dienophile. In the class 20 ACE, I ask, can the opposite happen? Is there overlap? The overlap is when the part of the two atoms that are going to be bonded, because we know in a Diels-Alder, you're forming two new sigma bonds between two carbons. And I want to know, well, if you take the opposite, will we still get the same bonding, the good overlap, between what? Between the LUMO of the diene. So that is psi 3, and sometimes I put psi star 3. And the HOMO of the dienophile. And I drew the cartoon of this overlap in the answers for the Class 20 ACE. I suggest you go ahead and see that. And because I'm going to skip ahead a little bit, because on the last page of the Class 20 handout, I asked, what about a 2+2 addition or cycloaddition? And there we're also drawing the 3D orbitals to see if there's good overlap or not. Okay, so you'll look at this, and then the last one is on page 4 of the Class 20 handout. Is there good overlap between the HOMO of a diene, or not a diene, HOMO of an alkene, which is the pi CC, and the LUMO of another alkene, pi star CC. So I might have misspoke, but if I have these two molecules, let's make them different, but it's still going to do the same type of cycloaddition. Okay, would this happen? Is this allowed? Same thing here. I'm asking up here for the purple, is this allowed? We know it works for this. Whoops. So this is check. There is good overlap. Okay. Page 2. Showed you the standard Diels-Alder and how to draw bicyclic molecules. Then I have considerations at the bottom, which has endo and exo. I do want to mention about endo-exo. Let me give you an example where it's neither. Okay, it sounds a little strange, but if I have something like this, or if I have this, plus a dienophile where we have two groups and they are opposite each other, CN and CN, you have to maintain that positioning. So the CNs are trans. In the final product, they have to be opposite each other. So let me show you how I would draw that. It's still bicyclic, but one has to be up, one has to be down. Now, if you don't draw it properly, and I'm confused whether you mean up or down, a lot of people draw the hydrogens as well. So there, this carbon, hydrogen is slightly up, the cyanide is down, and in this carbon, the hydrogen is down, this carbon right here. Hydrogen is down and cyanide is up. So while in the C and the double bond, the CNs are trans, we have to keep these CNs, it's not really cis or trans, but it's opposite. It is actually cis and trans because you have a ring, right? And you have trans substituents and you have cis substituents. These are still trans still. So in this case, I can't call the molecule endo or exo because one is endo and one's exo. Exo is the one that's up, endo is the one that's down, the substituent. So this is neither endo nor exo. Now, imagine if you had something like this. If you had, they're both on the same side. Okay. And now you could have endo and exo. Both on the same side. Okay, a little sloppy, but that is exo plus the endo going down. And then the hydrogens are going up. Okay. That's also on the ACE, by the way. There are examples on the ACE. Oops. Okay. Page 3. I show you a dienophile that it's a triple bond. Okay. And in the bicyclic version, there is no endo and exo because the two substituents on the dienophile end up being in the same plane in the final product. The molecule, in that area of the molecule, is flat. So there's no up and down with the bridge or below the bridge. Point number 3, I talk about S-trans conformation versus S-cis and gave you a couple examples. One of the examples at the very bottom, it was no reaction because the diene was locked in an S-trans conformation. There's no way to twist that molecule to get the two double bonds facing each other, which they are in the S-cis conformation. And then on page 4, we did show why a 2+2 cycloaddition does not happen because the HOMO and LUMOs do not have productive overlap to make a bond. One of the carbon-carbon potential bonds, there is a no match. They are out of phase. Okay. So this is a quick video. I do want to talk about one last thing, as long as we're talking about Diels-Alder. We should know how to do a retro Diels-Alder, okay? And so on the class 20As, there's a problem number 3. And let me take, let's take C, the one that's bicyclic. And my question on that problem is, what is the diene and dienophile to make this molecule here? NO2, and then NO2 going up. Okay, where did this come from? And so the comes from arrow looks like this. Okay. It's black and white on the ACE answers, but let me do this in color. Red dot, blue dot, right? You have to find actually this double bond right here. That double bond is part of the diene. So this half of the molecule is the diene. And so the diene, if you take a look at this example, see the 2 red dots are here. And so in the product, the 2 red dots don't have a double bond. But if we try to predict what the diene was, then yeah, the red dots do have the double bonds. So I am going to notice that this is 6 carbons. 1. Oh, let me draw the dotted line actually. This is where the 2 single bonds were made. And the numbering that I'll use here is 1, 2, 3, 4, 5, and 6. Okay, so we have a 6-membered ring, and we have a dot on carbon 6 and 3. Where do I want to put that? Let's put that here. Oops, red. No, let us number first because I'm getting a little bit confused. Oh man, 1, 2, 3, 4, 5, and 6. The red dots are on 6 and 3. 6 and 3. And the double bond originally in the diene now would be between 1 and 6. Okay, it worked, thank goodness. And 2 and 3. Let me draw this in blue. So this is your diene. Okay. The 2 blue dots are here and here, and that used to be the double bond. The dienophile is usually 1 double bond. But look at the NO2 groups here. There and there. They are opposite each other, so like I talked about up here, let's make the NO2 groups opposite each other. You could always give this to a classmate and say, hey, what is the product you get if I give you these 2 molecules, the diene and the dienophile? And if you draw this, you know you got it right. For me, when working backwards to predict where what diene and dienophile a product came from, find your double bond, mark your red dot and blue dots, and put your green cut line. Okay, we could do the same thing for all of our Diels-Alder. So here, the cut line is there. That's it for Diels-Alder. If you have any questions about the reaction or any concepts within it, this class, be sure to let me know. That's it for Module 8. The last Module 9 is about benzene rings and aromaticity, and those videos are forthcoming.